All right, thanks for having me. Yeah, I'm going to talk about code we're developing and working on called Open FUSION Toolkit, and this is a open source suite of modeling tools. So I'll talk about exactly what those are. And one of the key things is we're looking to try and have this span sort of what I think are at the moment the three sort of main stakeholders, which is the engineering, you'd say well, I'll talk about, I guess it's not the wording I normally have, but yeah, looking across engineering, analysis, and education and how this spans research, education, and industry. And there's some examples here on the front page. All right, so yeah, so this is a toolkit, right? So it's a suite of tools that are built on a common framework, and that framework is based around finite element methods for unstructured grids. So there's the QR code there. If you want to take a look at it, link at the bottom. Of course, everything's on GitHub, like many of the other tools here, right? So this code is written in a combination of Python, Fortran, C, and C++. So we just use C-types-based Python interfaces for our interactive and scriptable tools. And then we have a hybrid MPI, OpenMP parallelization with looking into GPUs for the future. And one of the things, as you'll see in the future, is that we have tools that span from kind of lightweight interactive tools to large HPC tools. So trying to have a framework that can span these areas is something that's, takes some effort. All of the tools, as I mentioned, use finite elements on unstructured grids, and the desire for us in the fusion space is looking forward to be able to capture engineering relevant features. So this is, the complex geometry that the previous speaker talked about, whatever the level of detail is that you need to capture to assess the thing you want for your fusion design. We want to make sure that the numerical methods can do that. We're also interested in finite elements so that we can do high, I have high in quotes here, order spatial discretizations, because we want to capture relatively large or relatively high geometric fidelity. We're already going to have a reasonable amount of resolution. So we're generally not interested in these very high order discretizations, but in general, in practice, we go up to about fourth order. And the key to doing, capturing these engineering features is being able to do some form of direct meshing from CAD. So this is sort of swiping over a lot of this. As anyone knows who's tried to do this, you can't just take a CAD engineering model and dump it into a simulation program. You still have to do defeaturing, all this kind of stuff. But being able to work with those workflows in the same way that commercial tools would. And this is a benefit of unstructured grids for these approaches. And we're really, in an open source way, trying to have a focus on usability and extensibility. So now I have it presented in the way I usually like to talk about it. So we're trying to look across these three stakeholders of the research community, which has traditionally been the big part of the fusion community, but also education, which of course has been integrated with research, and now more and more the industry. And so how can we have a tool that can be used across these spaces and hopefully be used as a bridge to enable interaction between all these stakeholders? And of course, the key is making it usable. So this is documentation examples, CI testing so that people can trust the tool. Also easy use. So in our case, because we have a lot of compiled code, this means downloadable binaries that people can just download. They don't have to build the code themselves, both for the release as well as because this is an evolving tool. You don't want people to have to always wait for a release. They want to be able to use, development resources as well. So having some sort of CD pipeline. And then particularly for industry, we need something that's sufficiently permissive. So in our case, we've gone through LPGL3, and this seems to be permissive enough. So we have several companies who are already using this. Okay, so I wanted to talk a little bit more I'll talk about the physics tools, but I also wanted to talk about some of the sort of software engineering mechanisms we use, just because I think some of the challenges are common across, and just wanted to bring these up in case people can benefit from these or people have other really good ideas. So for documentation, as I said, this is really key. So we use Doxygen to do this. Having this mix of languages across Fortran, C, and Python is really kind of a challenge. Most documentation systems are tailored to one. Doxygen, in my experience, is the closest it can be kind of cross code. And this tends to work pretty well for us. So this allows us to have in-source comments, specific markdown documentations, and also Jupyter example notebooks all integrated into a common documentation suite. And for me particularly, there's a lot of these that can do the integrated thing, but not necessarily with the in-source comments. And the in-source comments are really nice, in my experience, because if you're working then on code, your language server can pick this up and provide, for example, if you have documentation like this in Fortran, the Fortran language server will pick this up and give you, hover information on this subroutine, including the documentation. And so having this within your development environment, not only as like a separate window, is I think a really useful thing to have. And for those who don't already know this, if you do this sort of Doxygen or Ford-like documentation, it will show up in the language server. So then the documentation can be automatically built and published. Our online documentation retains several versions, and we also, have the head version. And we've had to generate some additional kind of scripts to make this work cleanly, or make like really nice formatted examples, particularly for Fortran. But it's really just like smoothing out edges. It's not large efforts there. And I'll just point out here, if you are using OFT or planning to use this, examples are a great way to contribute, because this is always a work in progress. And one of the best ways for people to learn how to use something is see a bunch of examples of different workflows. So along with, again, many tools, this kind of mixed environment creates a little bit of a challenge for some of the other things too. So we also have a fairly complete CI and CD workflows that we run through GitHub Actions. So on every single commit and pull request, we run, you can see here, I don't know, it's like 12 different CI jobs across different OSs, different compilers, with and without MPI, and different versions of MPI. And also, you can't really tell here, but this is a PETSI build down on the bottom. So trying to cover a lot of the different cases that people would run on, again, from this interactive space up to sort of HPC-like space, although on GitHub Actions, you can't run really very big jobs, so it's not really doing HPC testing. In earnest, we also track code coverage, compared to some really professional tool, right? This is going to be still pretty low. We're only in like the high 60s%. We're trying to push this forward. And then we have CD builds that build, again, binaries, release binaries on each commit to main across basically the common different environments that people would run on. These Linux ones are pretty much cross-platform across all of the different Linux distros. So everything is tested. There's about 400 tests per job. We also make sure that every main commit is signed. This is important, again, for people downloading binaries. They want to have some trust that the thing they're downloading is not problematic in some way, because it might have access to their system, at least at some level. All of our packaging, building, and testing is based on CMake, so it can be fairly easily automated with these sorts of existing workflows. We actually have a PyTest-based testing, which, again, similar to this Doxygen, allows us to actually run our test suite across all of the languages at once. And so we can simultaneously collect coverage and other things for these. And this is actually not that hard. It just takes a tiny bit of basically Python code to wrap over your Fortran testers. So this works fairly well. If you want to take a look, you can see it's up in the repo, of course. And then we have some custom scripts here to, again, smooth out the rough edges, because anyone who's worked with any of these tools knows that they're not as turnkey as they're put out to be initially. Okay, so that's sort of talking about some of the infrastructure work that we've tried to do to make this, a research tool more like a good, high quality open source tool, and particularly for things like Fortran that aren't often in those types of environments. So now talking about the main code itself. So there's this core library, right, that supports all the physics tools. And again, we're trying to aim to provide some level of scalability between high performance while also balancing this desire of extensibility and usability. So there's sort of three components to the core. There's the core mesh and geometry handling. We support unstructured grids of either tetrahedra and triangles, or hexahedra and quadrilaterals. This can be 2 or 3D, so you can, of course, have grids that are just triangles or just quads without the 3D elements. We also support curved elements and internal refinement, which is important for multigrid. And then, of course, this handles the domain decomposition when running with MPI. We also have core linear algebra functionality, which handles all the abstract vectors, matrices, linear, nonlinear solvers. And we have some of the solvers implemented natively, although those might be interfaces to libraries like SuperLU or things like this. And we also have a backend through PETSI that allows access to all those things available in that open source library. And of course, this continues handling task parallelization, communication, things like this. And then we have the core finite element functionality, which for us has basically two finite element representations. We're not super general. We have a Lagrange scalar finite element representation and a H-curl space vector finite element representation, which is one of these conforming element representations. And both of these are, like I said, generally used only up to about fourth order. And both of them have built-in support for geometric multigrid, which we use in some of our solvers for scalability. Okay, so I'll go through some of the physics modules pretty quick here. So we have sort of four of them at the moment. So the first one is TokaMaker. This is a scriptable, time-dependent, axisymmetric MHD equilibrium code. So it's called TokaMaker, but it works for any axisymmetric magnetic configuration. It doesn't just have to be a tokamaks. That was just a nice name that we came up with. So the key thing here is it's easy to script. We do all the normal stuff that a time-dependent equilibrium code would do. So forward and inverse equilibria, equilibrium reconstruction, we can compute linear stability and do nonlinear time-dependent evolution and supplemental analysis and things like this. So this is described in a computer physics communications paper here from 2024. And I'm showing some examples here where this is what, say, a typical grid might look like for ITER. This is a example of some stability study that was done by a undergrad at the time, now a grad student at Columbia. And this is an example of how we've been able to integrate these tools into education. So these are two examples from a design class that happened at Columbia University in the fall. This is a GIF at the top showing iteration of their design as they're designing this reactor. And then on the bottom is a time-dependent example demonstrating control against a VDE within some voltage bounds. So, the students over a few weeks were able to pick this tool up, and start using it as a design tool within this class. Okay, so ThinCurr is another tool that's developed on top of OFT. So this is a scalable thin wall electromagnetic modeling code for large scale systems of conductors, as you have in fusion devices, right? We have vacuum vessels and all these other things that can interact with our magnetic fields and other currents. So this models eddy current dynamics for 3D structures in the thin wall limit. You can do analyses like time and frequency domain runs, and also compute eigenvalues, which is often important early in the design cycle. Gives you access then to currents, voltages, magnetic fields, and force predictions. And this can also be used for something we're looking into is a finite element-based winding surface optimization here for stellarators. So in this case, this is a triangular grid. It uses a boundary finite element method. And we use a hierarchical off-diagonal low-rank approximation for the inductance matrix, which takes our n-squared scaling down to order n log n. So this is a fairly common thing in the boundary finite element world and gives us this scalability to large models. And this allows us to capture whole device models, and there's a paper on arXiv describing this as well. Okay, so I'll show some videos here. These are two lesser used components, so I'll just kind of go through this quick. So we also have a time-dependent nonlinear MHD code for general 3D geometries. So this has linear and nonlinear solvers, can do resistive or Hall MHD with single or split temperatures, so ion and electron separately. It also supports a fully meshed resistive wall model that we've used for some studies. And this actually uniquely uses a finite element representation using H-curl elements, which supports some unique boundary condition formulations. So here's an example of running a very complicated plasma domain. This is the HITIS-IU experiment that was operated at the University of Washington. And this is running a MHD model described here. We're also developing a 2D model at the moment, which will allow more sort of direct interactive usage for educational and other purposes. Okay, let's go forward. All right, the last tool we have is Marklin. This is a force-free uniform lambda ideal MHD equilibrium code, also for general 3D geometry. So this is a scalable either Taylor state or vacuum field solver that can do arbitrary 3D geometry as a Python interface now, but also utilizes multi-grid solvers for scalability. Here's an example of an application where this is looking at particle orbits within what are called plectomemes, which in this case is something like what was generated at the SSX experiment at Swarthmore. And actually, I'll take a brief history point here. So this tool here was actually OFT's starting point. The code was initially developed by the late Dr. George Marklin, who is my thesis research mentor. So initially the code was just OpenMP parallelized with linear H-curl elements only. During my PhD, I then extended it to MPI higher order elements and implemented the time-dependent MHD on the previous slide. And following my PhD, I sort of periodically continued to build physics modules on top of it as some need arose, because of course all the underlying functionality was useful, and the physics module often takes not much to do once you have that underlying capability. And then recently in 2023, we had this major push to open source. So this sort of formalized these TokaMaker and ThinCurr modules, which are initially sort of informal, and also merged the 2D and 3D code bases. So TokaMaker was initially a separate code based off sort of a 2D version of the core libraries. So this is also a useful thing. And again, some of these can be used for investigation, for education and things like this. And actually there's a paper under review right now for the results from this analysis that I'm showing there. Yeah, so just to conclude, the application of OFT is expanding across users in these three areas, so education, industry, and research. It's currently being used in the classroom. So at Columbia, we've used this in the Fusion Design, which is a grad course, but it's also being used in a course called Art of Engineering, which is an undergrad course where they try and introduce people to all the different sort of fields in engineering. So we're using this as an example of plasma and fusion engineering. I was also taught within the 2024 SULI Plasma course, I think successfully, and we have more of these things in progress, and happy to help anyone who might be interested in using this. It's also being used by industry, so I'm not going to name specific companies, but several fusion companies are applying OFT both internally and in research collaborations. So one of the things we want to do is have this as a bridge between these areas, and so it's been very successful in that area so far. And it's also being used in broader open research. So since the open sourcing a little over a year ago, it's already supported over 10 peer-reviewed publications and more than 30 presentations and posters that I know of. It's been particularly useful for research interns. So the result that I'm showing here, for example, is from a summer intern from last year, one of the members of the SULI program at Princeton, who did a study on accessibility of different shapes in NSTXU. So with that, I think I'm out of time, and thank you very much.
Excellent. Thanks, Chris. Really interesting tool, covers a huge range of different applications. Love it. Let's see, we do have one question here. Regarding your CI/CD infrastructure, what tools do you use to track code coverage? It's just looking at the GitHub repo, actually.
Yeah, so you can, I would say, like, yeah, take a look at the GitHub. So we use CodeCov, is, you know, who knows how you pronounce these shortened versions of things, but it's CodeCov, which is a website, right? And all that does is takes the output from Python's coverage module, and coverage then runs PyTest, and then basically afterward, what you get is there's two files. There's one from the GCC coverage suite that covers all the compiled files, and there's one from Python that covers all the Python files. And then CodeCov will basically grab both of those and put it up, and then gives you a merged report. So that works reasonably well once you figure out all the undocumented, you know, flags and things you have to do. But yeah, you can take a look at our workflow, and if you want to try that out, if you have any questions, let me know. But hopefully it's straightforward. Everything is up there. And I don't think anything is using like additional scripts or anything like that.
Nice. Yeah, that sounds very similar to what we do in OpenMC. We tend to use coveralls for whatever reason, though. It's just, you know,
yep. I would say, yeah, I would say if you are doing things like this with Python and compiled code, and GCC coverage, there is a trick that you have to, if you're loading from a library, you have to call a specific function at the end of execution to basically dump out the GCC coverage information. So that's really easy to do. But if you don't know you have to do that, you'll struggle for a long time being like, why don't I have any coverage?
Why your coverage super low or something, right? Yeah.
Again, that's in there. You can find it. It's really easy to do. But yeah, it's not easily documented.
Okay, we're going to try to capture one more quick question, and then we'll move on to our next speaker. We have a question from Matthew. Impressive talk. I love the focus on code quality. I'm curious about the choice to use a custom finite element library instead of an existing open source option like MFM or Phoenix. What was the motivation behind that?
Yeah, so this would primarily go to the history of when I did this code initially. I think Phoenix might have just existed back in, this was like 2012, but MFM didn't exist, or at least not that I was aware of. And so, yeah, we've periodically looked back at this. I think in the future, this might be something we do. I would say one of the challenges that I have found is that the libraries work really well and probably would work well for like most of the use cases here. But sometimes, especially for like the nonlinear MHD, when you're trying to do relatively big, tightly coupled models with like, different representations for different fields, they just, it's trickier to do. And so I'm not saying that doesn't work, but it's a big investment to figure out even if it would work well at the start. And we haven't quite gotten to that point. But it's definitely something we'll continue to consider. And I would really like to be able to switch to an underlying library at some point, because maintaining some of this stuff is a little bit of a pain. I mean, only when it breaks, right? But it can break.